Okay, so I'm going to pick it up from here. Even though this problem has a warning message, it works. So I'm going to work through it and make sure we can all do it. And you'll see that when you enter the problem, everything is groovy. Is this my crowd for the day? You seem exceptionally socially distanced. Okay, so where is the circle? R is equal to 6 sine theta. Tangent to the x-axis of a diameter 3. So it's, I'm sorry, diameter 6, radius 3. And that other circle is centered at the origin of radius 2. Something like this. We want inside this circle, but outside that circle. So we want in here. So we need to know these points of intersection. We find them by setting the two equations equal to one another. So we need to know where 2 is equal to 6 sine theta. Divide by 6 gives me a 1/3 over here. That's not one of the numbers that has our reference angles that we've learned, so we'll just have to say that that angle is the inverse sine of theta, or inverse sine of 1/3. Ah, come on, marker. That's the one in the first quadrant. The one in the second quadrant is pi minus the inverse sine of 1/3. Those will be the limits on our integral. But I'm going to go ahead, just use symmetry. I'm going to integrate from the arc sine of 1/3 to pi halves and then double it so that I don't have pi minus the inverse sine of 1/3 as my other limit of integration. Yeah, that sounds good to me. Then I write the area. In general, area looks like 1/2 the integral of f of theta squared d theta. But I said I'm using symmetry. So my area is going to be 2 times the 1/2, the integral of that lower theta, which was the arc sine of 1/3, up to pi halves to get the right half of that shaded region. Now, what do I do about my f of theta squared? Remember what we're doing when we're finding these areas. We're subdividing the region with sectors. So a typical partitioning element looks something like this. I'm going to drop big so you can see it. And so to find the area of this little circular region here, we'll have to go from here squared minus here squared. Okay? So the outer minus the inner. That gives me this integrand. The outer one is the shifted circle, 6 sine of theta. We square it. And then the inner radius was just the 2 squared. All right, so let's do all the fun stuff in between. Here I get 36 sine squared of theta. minus 4 d theta. Then we integrate term by term, and we have a formula for the integral of sine squared. So here's your pop quiz. What's the integral of sine squared? Good. That's going to be multiplied by 36. Then I'm going to integrate the 4 and get 4 theta. Then I'm going to put those two numbers in here. If I distribute the 36, I don't have to carry so many numbers around. So I'm going to go ahead and distribute the 36 and combine my thetas. This 36 times theta over 2 gives me 18 theta. Then I've got minus 4 theta. So that's 14 theta. And then 36 distributed here gives me 9. So minus 9 sine of 2 theta. That might be a little bit easier to plug in my two limits of integration. So notice when I plug the pi over 2 in here, that becomes the sine of pi. The sine of pi is 0. So when I plug pi over 2 in here, I get 7 pi. But now I have to subtract the value of that expression when theta is arc sine of 1/3. So I'm subtracting 14 times the arc sine of 1/3 minus 9 times the sine of 2 times the arc sine of 1/3. You can enter that into your web work as is. I'm going to go further. I can write the sine of 2 times the arc sine of 1/3 in a much simpler form. But I have to use a double angle formula for the sine function. Do you remember the double angle formula for the sine of 2 times angle A? What good are y'all? Y'all don't have got one bit. Doesn't have any, it has sines and cosines in it. Nope, that's a little more. That's a little too much. That's the cosine of 2A, so you get partial credit. Two sine of single angle A times cosine of single angle A. So I'm going to put that in right here, where my angle A is the arc sine of 1/3. So the sine of 2 times the arc sine of 1/3 will be 2 times the sine of the arc sine of 1/3 times the cosine of the arc sine of 1/3. I'll ask for your help again. What do you think the sine of the arc sine of 1/3 is? That is 1/3. They're inverse functions of one another. So these cancel each other out, and I just get the 1/3 back. Here I want to know the cosine of some angle that I take the sine of to get 1/3. This represents an angle. The arc sine of 1/3 is some angle that I take the sine of to get 1/3. So let's make a picture. Here's an angle that I take the sine of to get 1/3. So the cosine of that angle will be the adjacent side over the hypotenuse. So let's find the adjacent side real quick. Square root of 8. And so the cosine of the arcsine of 1/3 is the square root of 8/3. So now we can write this prettier. Let's write our answer prettier. That will be 7 pi minus, we said the arcsine of 1/3 was just the arcsine of 1/3. So I have minus 14 arcsine of 1/3. And then the three numbers multiplied together out there, I'm going to have a 9 times the 2 times the 1/3 times the square root of 8/3. So the 9 and the thirds cancel. And so the number at the very end is just 2 times the square root of 8. I said that was the pretty answer. You okay? And again, you can enter it here. I'm just doing this because later on in the semester, we're going to go this far as well. We're going to need more than just stopping right here. All right, anybody need to see any other web work problems? That was the one that had the warning message. It'll accept that answer if you type carefully. 7? Can you tell me what number 7 says?
It's the intersection of r equals cosine theta and r equals 2 sine theta. I think it's the intersection.
You want to find the area of the intersection or just find the intersection? Find the area of the intersection. Okay. So give or take the scaling factors, you've got some pair of circles intersecting here. In this example, the first circle is a circle of diameter 1 on the x-axis. And here's a circle of diameter 2 on the y-axis. So it's a messier version of the case that I ended class with. Let me draw the picture up here. Okay, so the first one, the second one is on the y-axis of diameter 2. First one's on the y-axis of x-axis of diameter 1. And so we want to find the area of that little intersecting area right there. So we need to find where they intersect. Find where they intersect. We need to make it a little bit bigger so everybody can see it. I'm going to rub that out and make it bigger. Y-axis circle. That arrow is going to be a 1. X-axis circle. There's that green line that I drew. That angle we're finding right now. Set the two equations equal to one another, and we've got the cosine of theta equal to 2 sine theta. I get a tangent in here if I just divide by cosine. And so if I solve for the tangent of theta, I have tangent theta is a half. That's not one of the reference angles either. So we'll just write that angle as the arctangent of 1/2. Now I made this picture bigger because I need you to see that for all angles between 0 and the arctangent of 1/2, this region right down there is what area we're finding. Between 0 is where this point comes in, to the arctangent of 1/2. In that region, the rays that are used to partition this sector don't hit the cosine curve. Every single ray I draw from the origin is going to hit the sine curve. Every single one of my partitioning rays. So I find that area with a sine curve from 0 to the arctangent of 1/2. But once I pass that angle, then my rays begin to hit the cosine curve. So from this angle until the cosine curve closes, what angle makes that cosine curve close? Pi over 2, right? Cosine of 0 is 1. Cosine of pi over 2 is 0. So from the arctangent of 1/2 to pi over 2, I find the area of the upper region. So it's not radially simple. We've got to do 2 integrals. So I've got to do an integral between 0 and the arctangent and 1/2, and then from the arctangent of 1/2 to pi over 2, a different integral. Area 1 plus area 2, where area 1 is going to be below that angle arctangent of 1/2, and area 2 is going to be above it. So when I'm below it, I have 1/2 the integral from 0 to the arctangent of 1/2. My integrand here again was the sine curve. So I have 2 sine theta all squared. Then the area from that green ray up to pi halves. Arctangent of 1/2 to pi halves of the cosine of theta all squared. Let me know if that doesn't make sense. Can't use symmetry because it's not symmetric. Our circles have different diameters. All right, so let's plow through the mundane steps. Squaring gives me 4 sine squared theta. And over here it's just cosine squared theta. I can go ahead and take 1/2 of this 4 and give you a 2. Then I'm going to integrate and get theta over 2 minus the sine of 2 theta over 4 from 0 to the arctangent of 1/2. This next one, I get theta over 2 plus the sine of 2 theta over 4 from the arctangent of 1/2 up to pi halves. Okay, and that first batch there, the 0 gives us nothing. Let's put the arctangent of 1/2 in and distribute the 2. So those will cancel, and I have the arctangent of 1/2 minus the sine of 2 times the arctangent of 1/2 over here. Pi halves is going to give us 0 here, but it still give me a number here. So pi halves over 2 is pi fourths times this half gives me pi eighths. 1/2 of 1/4 gives me an eighth out here. And then I'm going to have the sine of, I said that was going to be 0, and it still is. Okay, now I subtract. Put the arctangent of 1/2 here, so I'm going to have minus 1/4 of the arctangent of 1/2. And then minus, since I'm subtracting the lower limit, 1/8 out here of the sine of 2 times the arctangent of 1/2. We can kind of combine some of these.
1/2 on the first side.
1/2 on the first sine. Yes. Miss anything else?
We could just input that whole.
You can.
Yes.
You can input this. This will combine, right? This one and that one gives you 3/4 of the arctangent of 1/2. And this one combines with that one to give you what that's 4/8, 1/8 minus 5/8 of the sine of 2 times the arctangent minus the arctangent of, you can just put it in like that. We can do all the steps that we did a second ago and get fractions for those sines of the 2 arctangents.
Like this.
You can leave it like that on the test. I'm never crazy enough to give something like this on the test. Happy? Doesn't take much to make you happy, does it? Ready to go on? Something new, something new? Let's find arc length. We'll go back to rectangular coordinates though. So we're on section 6.4. I don't know if I started it for you last time or not, so I'll just talk like I didn't. We're going to find the length of a curve in rectangular coordinates, and then we're going to find the length of a curve in polar coordinates. There's a piece in here about finding surface area, which is kind of a 3-dimensional version of length of a curve, but we're not going to cover the surface area part of this section because it's covered again for you in Calculus 3 when you actually have these 3-dimensional surfaces and with a much easier approach to it. So just do the arc length parts of section 6.4 and ignore, if you're reading along in the textbook, discussion of surface area. I used to like to cover surface area so you could see by the time you get in Cal 3 how much easier it is in Cal 3 than it is in Cal 2. But then that just propagates the myth that Cal 2 is the hardest calculus, and I don't want to do that. So I skip the hard stuff. Okay, arc length and length of a curve, yes. The hardest calculus concept that I can explain to you. Like, so that you'd understand it, or so that I was telling the truth? That's a tough question. I'm really lousy at some of the physical interpretations of some of the things in Calculus 3. Right? In Calculus 3, some of you engineers, maybe down the line, are going to study something called flux and curl. I know the calculus of it, but I just don't really get the physics of it. So whenever I do teach Cal 3, I just kind of read something and pretend I understand it. But I really don't. So when the calculus and the physics start doing that, I just, ooh. So that was an honest answer. Probably the other thing that would be hard in your eyes, if some of these theorems, we actually did the proofs of them. I do derivations when it involves algebra, but when you have to prove things, you'll probably just, eh. I understand that too. Any math majors in here? Yeah? We get most of our math majors after they get kicked out of engineering for falling below the 3.0. So I hope I don't see any of you again. I'm not lying. We have 385 math majors. They didn't all come to Tech saying, ooh, I want to study math. Okay, so here's a curve. Y is equal to f of x. And I want to measure how long it is from the ordered pair A, f of A, to the ordered pair B, f of B. So I get out a tape measure and I lie it on there. I take that as a string, cut it, stretch it out and measure it, and there I have the length of the curve. I can't do it that way. So instead, in calculus, we find the length of the curve by taking that arc and cutting it up in a bunch of itty bitty, teeny tiny intervals. Put a bunch of points on here, close enough so that between any 2 points, the curve itself looks like a straight line. So if you went up maybe over here, that looks almost like a straight line. I'm going to squeeze them real close together so that it essentially is a straight line. And we'll squeeze them close enough together using a limit. So I look at some partition of the interval on the x-axis from A to B. So x1, x2, x3, x4, blah, 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 out to the kth partition. Say that this corresponds to xk and xk plus 1, so that the ordered pair here is xk, f of xk, and the ordered pair here is xk plus 1, f of xk plus 1. I have those points close enough together so that the distance between them is the linear distance between them. Those points are on a curve, but when we're close enough, that curve looks like a straight line. The distance between 2 points on the line is just the Pythagorean theorem. That's the hypotenuse, where the legs have a change in x and change in y. So the length of that hypotenuse is change in x squared plus change in y squared under the square root sign. Okay, so by the distance formula or the Pythagorean theorem, the length of, let's call this pk plus 1 of interval pk plus 1 as a line segment is just change in x squared plus change in y, those are all k's, squared under the square root sign. Then to get the arc length of the curve, so the length of the entire curve on that interval from A to B is an infinite sum of these. From k is equal to 1 to infinity of things that look like that. Well, make the infinite sum look more like a Riemann sum by putting the letter n here, and then we'll put the limit out here as n goes to infinity. So you know that's going to come out as some sort of integral, but I've got to manipulate this a little bit to make it look like an integral. And the way I do that is I'm going to factor out the delta xk squared from those two terms under the radical sign. That'll leave me a 1 in that slot and a delta yk squared over a delta xk squared here. Then I can take the square root of that, and it comes out here as a delta xk to the first power. And I'm going to group that as a quantity squared. So that's the thing that's going to look like our Riemann sum, and the fact that on every interval of a continuous curve, somewhere the average rate of change is equal to the instantaneous rate of change, mean value theorem. So I can replace this with the derivative, and my integrand would have the integral from a to b of the square root of 1 plus y prime squared, and this becomes the dx. Where y prime would be written as a function of x, so this integrand is a function of x. We can do the same steps, factor out the delta yk, and make this a dy integral, and then we would integrate from the range of the y value. So that's no big deal, but it'll look the exact same. We'd have an x prime as a function of y and a dy here. And so that's the length of the curve, and it'll be designated with a lowercase s. Remember that formula, because in calculus 3, you're going to parameterize some curves in terms of s, in terms of its arc length. It's just the distance formula. Now, it involves calculating an integral with a square root sign. And I warned you that there aren't many of those that we can do. So let's start with a linear function. Those are easy. We don't even need an integral to do that. Let's find the length of a line segment two ways. One way with our formula, one way with just the distance formula. Let's take y is equal to 9 minus 3x. And I want to find the length of this curve from x is 1 to x is 3. So the easy way, then we'll do it the integral, we'll get the same answer because life is good. If I draw you this on that line segment, when x is 1, y is 6. When x is 3, y is 0. So it's the line that goes through 1, 6, and 3, 0. So it's the length of the hypotenuse of a triangle where one leg has length of 6 and another leg has length of 2. So the Pythagorean Theorem tells us that this length is 6 squared plus 2 squared under the radical. 6 squared is 36 plus 4 is square root of 40. Now let's use our brand new, never been used integral. Here is y. So y prime is just -3. So we're going to integrate from x is 1 to x is 3 1 plus -3 squared dx. Using our formula, arc length is the integral from 1 to 3. 1 plus y prime squared, so y prime I said was -3 times dx. So let's see, that's 9 squared, 10. So I get the square root of 10 times x, but x becomes 3 and then 1. So I get 2 times the square root of 10. How close is that to the square root of 40? The same, right? Okay. Let's do one where we can't use the Pythagorean theorem. Let's just take something else. Find the length of, let's go with y is equal to 1/12 x cubed plus 1 over x on the interval from x is 1 to x is 3. So see, you gotta have something kind of funky looking so that my integrand will simplify. On 1, 3, this is a nice continuous curve. I just don't know what the picture looks like, and I really don't care. I do need the derivative of that. I'll put it there and square it. So let's go ahead and take a derivative. Derivative of x cubed is 3x squared. Now it's your turn. What's the derivative of 1 over x? Negative 1 over x squared. You got to keep your derivatives and your antiderivative straight. The derivative of 1 over x is a negative 1 over x squared. So this will simplify to a 1/4 x squared minus 1 over x squared. Okay? You can even write that as a single fraction if you want. I don't care how you do that. But our arc length formula now has this square root sign, 1 plus the derivative squared as a function of x. So we're going from x is 1 to x is 3. 1 plus that thing. It's possibly easier to square if we wrote that as a single fraction. So if I got a common denominator between those two, I can write that as x to the 4th minus 4 over 4x squared. So why don't we put that in here and square it that way? Is that any better? I don't know either. Now let's just square from here, square from there. Okay. Okay, I'm going to do that. I'm going to square it. That's just algebra, so you got to watch me, make sure I don't muck this up. Before I do the algebra, why can't I just say that this is the square root of 1 plus the square root of that squared and get rid of the radical sign that way? Can't distribute the square root sign. You're going to try to do that. You're going to be sleepy. doing problem and you say, okay, that's just 1 plus x to the 4th minus 4 over 4 squared. Those are both perfect squares. Can't do that. Freshman algebra. Okay, so I've got to do the squaring, and then I've got to combine these terms. So I'm going to square this as a binomial. I'm going to square that and get 16x to the 4th. So what is x to the 4th minus 4 all squared? Spell it out to me. Everybody agree? And then I've got the 16x to the 4th on the bottom. Then I've got plus 1 here. Then I've got the square root sign and the integral sign. Lost my dx, I need that. We still can't integrate, right? So I'm going to get a common denominator. I'm going to write this as 16x to the 4th over 16x to the 4th so that I can combine these. With me there? So adding the 1 by getting a common denominator. Now I've got 2 common terms, so I can add those. And so I have the integral from 1 to 3. I'm going to put it in descending order. I'm going to have x to the 8. We get a plus 8x to the 4th in the middle. Plus 16, all divided by 16x to the 4th. Are you with me to that? Here's where the magic happens. These problems are contrived in such a way that you got a perfect square in there. Factor x to the 8th plus 8x to the 4th plus 16. Should factors a perfect square. Factors of x to the 4th, x to the 8th would be x to the 4th times x to the 4th. Factors of 16 with the same sign that add to 8 will be 4 and 4. So this numerator factors as x to the 4th plus 4, all squared. That should happen in every one of your problems. You should have a perfect square somewhere, or at least some way to get a u/du integral. So now both the numerator and the denominator are perfect squares. Nothing's added anymore. I can take the square root of each term, and I get x to the 4th plus 4 over 4x squared left to integrate. Now I have to separate those in order to integrate this. I'm going to separate that as a 1/4 x squared plus 1 over x squared to integrate that. All right, the 4's would cancel here. We need a 1 over x squared. Here the x squareds cancel. We need 1/4 x squared. You got to write that as x to the -2 so that you can integrate it. And you will get, guess I'll put it up here. (1/4) x cubed over 3. I said this is the same as x to the -2. So when you integrate that, you get negative x to the -1. So a -1 over x to be evaluated from 1 to 3. Okay? So these problems are such a way so that we will somehow be able to get rid of the square root sign, or at least be able to write it as a u/du integral. You've got to look for that. And once we learn how to do more integration, then we'll do some other sparkly problems that we know how to integrate after we finish chapter 7. Now, the polar version of this formula comes from x and y being functions of theta. So remember that in polar coordinates, x is equal to r cosine theta and y is equal to r sine theta. Or r itself is some function of theta, right? R is the dependent variable, theta is the independent variable. And so if I took the derivatives of these with respect to theta, I can write dx d theta. Do I want to do it in theta instead of like that? Yep, I do. Right? In our problems, r is some function of theta. So dx d theta by the product rule would be the first times the derivative of the second plus the second times the derivative of the first, which I'll write as dr d theta. Same deal with the y. dy d theta be the first times the derivative of the second plus the second times the derivative of the first. And our arc length element, which remember had the change in x and the change in y in each slot squared. Oh, I want to write that. Well, I don't even want to write that just yet. All right, I had the change in x squared plus the change in y squared. So keep that in mind. So when I square these things, dx d theta squared plus dy d theta squared involves lots of algebra. But when you square this and when you square that and you add things together, you're going to eventually get an r squared cosine squared added to an r squared sine squared. What's sine squared plus cosine squared going to give you? So you're going to end up with an r squared, right? So you're going to get an r squared under your integral. And then you're going to have some version of this, which would be kind of like the r prime squared, because you got sines and cosines. You're not going to get any middle terms, because when you do the squaring in here, the middle term is the same as this middle term, but opposite. So you're not going to get any middle terms. So your formula is going to have some version of an r squared and an r prime squared in it. And that's what you do get. You get in polar coordinates, you can have some version of an r squared plus an r prime squared. And you'll integrate with respect to theta. So our polar coordinates, polar form for arc length, will have an integrand that looks like that. It'll have a square root sign, and it'll have your r squared here added to dr d theta squared here, and then a d theta. So you're not going to have the 1. You're going to get an r squared, and that again comes from squaring that and adding them together. Let's skip those steps. I'll do an example next time of finding polar length of a curve, but that'll at least arm you with enough information to try to find yourself before you do an example. Okay? Any questions from you guys at home? Anything you guys want to ask?
Yeah.
All good? All right, I'm gonna catch you off then.